Welcome to the fifth video in a series of 8 on rational expressions. Addition. Notice that addition and subtraction were saved for the latter portion of this series, and that's because they're the most difficult operations, compared at least to multiplication and division. So here comes a slightly challenging set of problems. Before we can do an actual problem like you might see in an algebra class, we're going to look at an example of how to add two numerical fractions. You may recall that adding fractions is not as easy as simply adding the numerators and adding the denominators. This is incorrect, but worth mentioning because it's so common that people do this. That adding fractions works differently than that. To add fractions, we need the rule of a common denominator. And we need these two numbers in the bottom to match. A quick way to do that is to try to think of a number that is both divisible by 6 and divisible by 4, and preferably to make that number as small as possible. Well, a little thought will convince you that 12 is the smallest number that's divisible by both 6 and 4. So what I'm going to do is try to change these fractions into twelfths. Well, how can you just change the denominator of a fraction? Well, you can do it without changing the value of the fraction if you multiply the fractions by 1. Watch as these elements come from the side of the screens. In this video, when you see fractions flying in from the left and right, that should always remind you that we're using the multiply by 1 trick. 2 halves is 1, 3/3 is 1, and by multiplying by these two versions of 1, we get fractions that look different than the original fractions but actually aren't, because those two fractions have the same value and these two fractions have the same value. So I appear to have changed the problem, but I've only changed its appearance. Numerically, I haven't changed it, but I have made it so that the denominators match. And once your denominators match, you keep the same denominator and add the numerators, which gives me the final answer to this problem. But our focus today is going to be on the addition of rational expressions, not just numerical fractions. In other words, we're going to be adding fractions, but they're fractions with algebra symbols in them. First of all, notice I don't have a common denominator here. And that's the biggest problem in the addition portion of this series. It's very rare that your denominators will ever match, so we won't give an example like that. Well, let's focus on what do you do if the denominators don't match. Well, to get them to match, to get that common denominator, it will be really helpful to factor the denominators. And that's what I've done right here. Now, once your denominators are factored, the second step that I like to do is more of a mental step, but I like to decide what is missing from each denominator. Now, what do I mean by missing? Something is missing if it appears in one of the denominators but not the other. For example, in this denominator, you'll notice that there is no x plus 3 in this denominator. I call that the missing factor. By the same logic, this denominator does not have an x plus 5, so I call that the missing factor in the fraction on the right. Now, once I have decided what's missing, and again, that's a mental step, you don't have to write anything for that. The third step is to multiply the fractions by 1. This will get us a common denominator. The two things that just flew in from the sides, those each have a value of 1, and notice that they have the effect of replacing what's missing in the denominator. By choosing these 1s and multiplying the fractions together, I will get a common denominator, as you're about to see. So I've multiplied the fractions together, which is essentially just physically putting the factors together, as we know from prior videos. But it's important to notice here that my denominators do in fact match. Of course, they're in different order, but rearranging the order of factors does not change the value. of a mathematical expression. So they do effectively match each other. So now I've achieved a common denominator. Now what I've done here is something a little unusual. It's unusual in the sense that I've multiplied the numerators out in so-called expanded or standard form. Likewise, I multiplied the numerators here. But notice the denominator I didn't change. Now, could I have multiplied the denominators out as well? Well, I did it on scratch paper. I wouldn't expect the average student to know where I got any of that. I basically used FOIL twice, and that's not something we're going to do in this problem. But I wanted to discuss why there's no reason to multiply out the denominators. Because, well, let me put them back. Because our next step in adding fractions, once we have a common denominator, is to keep them the same and add the numerators. So I needed to multiply out the numerators to get them to be in expanded form so I could combine them. But the denominators, I'm just going to keep the same for the rest of the problem and not worry about it. So while I could have multiplied them out as you saw me do, there's no reason to. Okay, so I've converged this into a single fraction, adding the numerators together. And now step 5 is to simplify if possible. Well, you'll notice in the numerator, the 3x and the 4x are combinable. They make 7x, and that is the simplification that I can do here. That completes that first problem. So I'm going to keep those 5 steps up there as a reminder each time of what we're doing. Here's the next problem. If you watched video 1, you actually saw a brief mention of this problem where I purported that it simplified to 4x plus 9 over 4x minus 4, which it does, and we'll see that in this video. Here are the details. Let's go through the 5 steps again. Step 1, I want to factor my denominators. Well, only one of them is factorable, you'll notice. Step 2, I want to decide what's missing. Well, what's missing over here is a factor of 4. Remember, when I say missing, I mean missing factors that are preventing the denominators from being the same. Okay, what's missing on this side? Nothing. So what I'm going to do is I'm going to multiply by 1 to get my denominators to match. But I only need to use 1, 1 here in the form of 4 over 4 because that makes the denominators match. So you don't necessarily have to multiply both fractions by a version of 1. So I've multiplied the fractions together, and now I'm ready. By the way, notice the denominators do match, which was my goal. I now have a common denominator, and now I'm ready to keep my denominator the same and add the numerators. Okay, I've merged it into a single fraction, I've kept my denominator the same, and I've added the numerators. Step 5, simplify if possible. Well, it's not possible to simplify this, so I'll leave it. And that is my final answer. You may recall I mentioned that this problem came up in video 1, where we got this answer, also a correct version. You'll notice they don't look the same, the two answers, but they are mathematically the same. Either one of those would be fine. There's no standard rule on whether you should multiply the 4 through the x minus 1. In other words, there's no accepted tradition as to whether you should have standard form or factored form in your numerators and denominators. So either one of those is fine. Here's a problem that's going to prove to be challenging for reasons you'll see in a minute. Let's go through our 5 steps. Step 1, factor the denominators. Done. Let's look at what's missing in step 2 here. Well, before we do that, looking at the 4 and the 6, one could say that there was a 6 missing from the left side and a 4 missing from the right side, and you wouldn't be wrong. But it's actually more efficient to think about these factored out monomials in terms of least common multiple. In other words, I'm going to ask myself, what are 6 and 4 both divisible by? Sorry, what number is divisible by both 6 and 4? And the answer to that, of course, is 12. So if I could turn both of those into a 12, it would actually make the math easier. So what's missing on this side is a factor of 3. Of course, there's also an x plus 7 missing. But let's focus on that 3. I'm thinking of that as a missing factor because if I multiply that into the bottom, my 4 will become a 12. And what's missing on this side, of course, there's an x plus 5 missing, but there's also a 2 missing. In the sense that if I were to put in a factor of 2, my 6 would become a 12. So that's going to guide me to choose my 1s. Here I'm multiplying each fraction by 1, and this will get a common denominator. If I multiply everything out, which is essentially just physically putting everything together, I get this. Notice what I did with the 3, 4, 6, and 2. I multiplied those out as 12s. That's a little strange. If you need to see that again, this would be a great time to rewind and hear it. That was a very tricky math step. Moving on, the denominators do match, so I'm ready to proceed to step 4 after multiplying all this out. Sorry, still on step 3. Notice I've multiplied these together, but I've also multiplied these together, but I didn't show the work here. I did it on scratch paper. If you'd like to pause the video to see all the details of where that came from, get ready to pause. Now's a good time for that. If not, let's focus on the bigger picture. Now, for step 4, now that I have a common denominator, I'm going to keep that denominator the same and add my two numerators together. And when simplifying, you'll notice in the numerator that there are a few pairs of like terms. The 3x and the 12x are alike, and the 21 and the 10, the constant terms, are also alike. Combining all like terms gives me my final simplification, and that is the simplified version of this problem. Here's another problem. Let's go through our 5 steps. First, we'll factor our denominators. Now let's decide what's missing. Well, one thing that's missing on this side is clearly an x plus 2. And one thing that's missing on this side is obviously a 3 plus x. But if I were to just multiply by this version of 1 here and this other version of 1 here, I wouldn't exactly have matching denominators. I would almost have matching denominators, but notice these two factors don't match. You may have heard me call them reversed subtractions. They're technically called opposite binomials. Whatever you call them, they're not the same. They're opposites of each other. Now, one way, which I don't recommend to account for these differing factors, is to consider each one as missing from the other side. But you're going to make a huge algebra mess for yourself if you do that. The better shortcut is to multiply by 1 in the form of -1 over -1. Now to do this, I could multiply the left fraction by -1 over -1, or I could multiply the right fractions by -1 over -1. Either one of those is fine, and it doesn't matter which one you do. And because it doesn't matter, I'm going to choose the left set of fractions to multiply by -1 over -1. Now, if you don't see why this works, watch it and you may catch on. So next, I've multiplied everything together, although that in this case really just means I've physically written everything next to each other in factored form. And now the question you have to ask yourselves is, do these denominators match? They sure don't look like they match. Let me convince you that they do. First of all, each denominator has a 3 plus x factor. Each denominator has a factor of x plus 2. But they appear to differ here. But they don't really differ because it turns out the green factor times the green factor is the red factor. And that is ultimately what makes this a great shortcut for dealing with reverse subtractions when they appear in an addition problem. Now that my denominators match, I've decided to write them both in the simpler way. And notice I've multiplied here, and I've multiplied here, and I've kept my same denominator. Again, it looks like I changed the denominator on the left, but those are really algebraically the same. Now I can go to step 4 and keep my denominators the same and add my numerators. And now on to step 5, simplify if possible. Well, you'll notice in the numerator there are some simplifiable components in that I can combine like terms. Combining like terms gives me this, and that is the final answer to this problem. Now, even though I'm done with the problem, I'd like to throw in an afterthought for the most courageous among you. I would personally put this as an answer instead, not because it's necessarily better, just because it's neater. Notice what I did from the first answer to the second is I found two factors in the bottom that were conjugates, and I multiplied them together to get x squared minus 9. Now, I normally wouldn't bother to do this, but in the case of multiplying binomial conjugates, it makes the thing look so much simpler, I think it's worth doing. By the way, no professor or teacher or website would ever care whether you did that or not, and so this last step is completely optional, just something I wanted to throw in there as a way to neaten up the answer. If it lost you in any way, set it aside. It's not a big deal, and nobody would ever expect you to do that last step that I personally did. And that completes the 5th of 8 videos in this series.